Welcome to the Goodman Memorial Lecture 2016. My name is Anneli Sundin and I work at the Stockholm Environment Institute. I received the exciting opportunity to coordinate and design this seminar with an interesting group of people from SEI, from the Royal Swedish Academy of Sciences, and from Stockholm University. Let's see, next slide. There we go. Yeah. Gordon Terence Goodman was originally from the UK. He grew up in Wales. And he was someone who was fascinated in nature as a child. And this fascination would take him onto the path of becoming an ecologist and a researcher. He was a creative thinker and a very skillful communicator, which enabled him to reach politicians, industry, and the local community to teach them about sustainable development. But one can wonder, how did Goodman end up in Sweden? He was rewarded a fellowship that allowed him to spend lengthy periods of time in Sweden to learn methods of detecting and measuring organic mercury in aquatic environments. In 1977, he became the founding director of the Bayer Institute at the Royal Academy of Sciences. Back then, the Institute had a research focus on energy systems, which is interesting considering the topic of today. Years later, in 1989, the Swedish government set up a new environment and development research organization called the Stockholm Environment Institute. Gordon Goodman was invited to become its first director. It was an inspired choice, as much of the work and many of the staff of the Bayer Institute moved to SEI, and new work and new topics took form, such as sustainable agriculture, biotechnology, air pollution, and much else. I won't tell you much about the research of SEI. Rather, I would like to tell you what SEI means to me. There are three things: diversity, passion, and impact. SEI is a workplace with great diversity, not only in terms of research, but in terms of views, experiences, skills, and attitudes amongst my colleagues. And we're always generating ideas, which SEI is very good in harnessing and supporting. My colleagues are also passionate about their work. In fact, they're very passionate about life overall, and they're passionate about this planet and our environment. Even though this passion sometimes results in too long hours spent at the office or out in the field, we've seen that it leads to impact, which is my third point. SEI's work is about impact. We're actively working with governments and academia around the world, but we're also fostering deeper collaboration with finance institutes and the planning and the private sector. We're also supporting long-term engagement in strategically important processes, such as with the UNFCCC and Agenda 2030. So as you might have understood, I really enjoy my job. And it is with big excitement that I'm kicking off this seminar. We're very happy to have Professor Daniel Nocera here, and it's a great opportunity for all of us to get enlightened on the groundbreaking research of artificial photosynthesis. It was an easy choice to have him as this year's Gordon Goodman lecturer. Not only is his research absolute cutting edge, but his research is also challenging policy structures, and we very much look forward to hear more about this today. The program will start by Professor Nocera's lecture, which is then followed by a scientific discussion. There will be a coffee break after that, and lastly we'll have a debate with an extinguished panel, and the event will finish with a mingle. Throughout the afternoon, you'll get the opportunity to ask questions, so please don't be shy. Now it's time for both Göran K. Hansson from the Royal Academy of Sciences and Anders Karlhede from Stockholm University to greet you. Welcome.
Thank you, Anneli, and good afternoon, everyone, and a warm welcome to the Royal Swedish Academy of Sciences on this sunny September day. I'm Göran Hansson. I'm a professor of medicine and secretary general of the Academy. And we here at the Academy are proud to host the Gordon Goodman Lecture. It's one of the rather few named lectures given here at the Academy. The lecture reflects on our strong commitment to research on environmental issues, resilience, and the biosphere. And that started several decades ago with Gordon Goodman, Bert Bolin, and several others. And with the generous support of the Kjell and Märta Beyer Foundation, the Beyer Institute was founded here in 1977 with Gordon Goodman as the first director. And a few years later, he and Bert Bolin initiated a process that led to setting up the IPCC, the Intergovernmental Panel on Climate Change, that was awarded the 2007 Nobel Peace Prize. Today, we have several research institutes at the forefront of environmental research here in Sweden and here in Stockholm. At the Academy, we host the Beyer Institute for Ecological Economics and the program Global Economic Dynamics and the Biosphere, which is supported by the Erling Persson Family Foundation. We have also helped founding the Future Earth program that has one of its international hubs here in Stockholm and actually in the building. With our partners at Stockholm University, we are involved with the Stockholm Resilience Center, and of course we also feel a strong commitment to the Stockholm Environment Institute. The Academy is well suited to host and help fostering research on environmental issues, since that kind of research often requires a cross-disciplinary approach. And we are truly cross-disciplinary here, with members from mathematics and physics over the life sciences to the social sciences. Furthermore, this type of research, of course, helps answering and addressing some of the major global challenges facing society today. And it's in line with the vision of our founding father, Carl Linnaeus, who has been called the father of ecology. So with that, I welcome you again to the Gordon Goodman Lecture, and we all look forward to hearing Professor Daniel Nocera in a few minutes. Thank you.
On behalf of Stockholm University, I would like to welcome you all to this year's Gordon Goodman Memorial Lecture. And in particular, I would like to welcome Professor Nocera. The title, The Artificial Leaf, connects environmental science and chemistry. And this area is an area where there is hope for solutions to some of the most daunting problems and self-inflicted problems of mankind. Chemistry and environmental science are two major research areas at Stockholm University. And we are proud to organize this event together with the Stockholm Environment Institute, with which we are developing our collaborations, and with the Royal Academy of Sciences, with which we have the long-term collaboration. So, welcome. And I would finally like to introduce the next speaker, which is Professor Lennart Bergström, a materials chemist from Stockholm University. And Lennart is also Dean of the Chemistry section of Stockholm University, and I'm Dean of the Faculty of Science. I'm also Deputy Vice Chancellor. We have a problem with titles at Stockholm University, particularly in English. So Lennart is a colleague of mine in the leadership of the Faculty of Science. So, most esteemed colleagues, welcome, Lennart.
Thank you. This one? Okay. Welcome, everyone. I will say a few words about Daniel Nocera before you have the chance to start your speech. We are currently confronting the opportunities and challenges of a global energy transformation. Several of the previous speakers have alluded to that. And this is, for example, reflected in wide changes in the marketplace, and of course also in a lot of political demands and commitments to minimize the use of fossil fuels in the near future. This is a grand challenge. And science is trying to respond to that today by developing different viable routes to solve this problem. The lecture we're going to hear today connects directly to this. Professor Daniel Nocera, the Patterson Rockwood Professor of Energy from Harvard University, is one of the world's leading scientists in renewable energy. His group has pioneered studies of viable technologies for the use of sunlight to produce hydrogen, eventually fuels from water and carbon dioxide. This is something which, in not a too distant past, seemed like a dream, but now seems to become a reality. Much of this work is inspired by photosynthesis, but also some of this work has really gone beyond what plants today can achieve. Some of these concepts have been formulated in the concept of the artificial leaf and the bionic leaf, which you're going to hear much more about from his lecture. Daniel Nocera is not only a very esteemed scientist with more awards than he probably remembers himself, but he's also very much engaged in the discussion about how science should be conducted. This is really important when we think about the challenges to, for example, to provide the world with a cheap and abundant energy, and not the least to the emerging world. Doing so, he has also been able to transcend some of the common distinctions between basic and applied science and showed a path, I think in particular for the young scientist, how this can be fruitfully combined into innovative science. With that, I would like to welcome you to the stage and look forward to your lecture.
Thank you, Lennart. So it's a pleasure to be here, and I'm very thankful to the Royal Swedish Academy, Stockholm University, and certainly Stockholm and the Stockholm Environmental Institute for inviting me here and to talk about our latest discoveries. And what I'll do, this is a more general audience. I had a really scientific talk, and Anneli looked at it and said, "Are you sure you want to give that?" And I know, she didn't say that. She just looked at me quizzically. So what I did is, there's going to be science. There's going to be a lot of science in here. But I want to make it available to everybody. And so luckily we'll have a lot of discussion at the end. And I want to just lead you on a path of what we did for discovery in terms of trying to emulate artificial photosynthesis. Am I going backwards? Okay, good. So I'll talk about a complete artificial photosynthesis, and I'll explain what that means in a minute. But it's from A to Z. So I think what we've now been able to do is the entire cycle of photosynthesis. And it combines lots of different areas of science. So there's an applied physics piece, there's certainly a chemistry piece, and then you'll see there's a biological piece. And I'll explain why we chose each of those pieces in trying to solve this problem. First, I'm just going to give a few general slides, and because first you should, especially the young people, choose your problem. And to choose your problem, this is what actually the Stockholm Environmental Institute does, Environment Institute does well, is it looks at a system and it thinks about systems. And once you understand the system, you can work backwards to say, where should you invest your time in research? And so I want to at least build the problem for you about why we chose the problem we did and the type of science we're doing. So this is an identity relationship. And so it's not an equation. This is exactly that. It's an identity. And it's saying that the amount of energy you use only depends on 3 parameters globally. and that is population, how many people there are. Gross domestic product per person, so how rich a country is, will determine your energy use. And then this is an interesting number, because when you hear about conservation, you might think it's a wishy-washy term. It's conservation. It sounds subjective, but it's actually an objective number. And what it is, conservation is energy per GDP. So if you're a country, you're Sweden, you try to hit a gross domestic product. And to get to that gross domestic product, you see that energy scales with money. So to get to a certain level of money, you have to use a certain amount of energy. Next year, if Sweden hits the same GDP and uses less energy, I can tell you quantitatively how much energy Sweden conserved last year. All right? So conservation that's called energy intensity. So when you take this and multiply it out, numerator, denominator go away, numerator, denominator goes away, energy equals energy. So that equation explains a lot. It also says you just can't be a scientist, because I'm going to now use different words. Science and engineering, energy intensity. GDP per capita, that's economics and policy and business. And N is sociology. So if you want to attack the problem comprehensively, it's good if you're a scientist to connect with these pieces also. So one thing I'll urge, because I've been here now for 2 days and I've got to be around SEI, a lot of the scientists, it might be good to start connecting to SEI, because they can help you with these pieces and put a context into how to do and what type of science you might want to do. But in our group, we've tried to take all of these into account, and that starts a set of science problems. So what I can do is calculate the amount of energy used, because I can just do Google. I do Google research. My students do real research, and now I'm so old, I sit at my desk and I just look on Google, and I do Google research. And so you're going to hear a lot of Google research in the front end of this talk. And I can look at the number of people per country. I know what populations are. I know what the gross domestic product is. And I can make an estimate of energy intensity, and therefore I can calculate the amount of energy used. To check the equation, I can go backwards. So in 2012, the world used 16 terawatt equivalents of energy. And I want to be a little careful here. Energy is joules, and I'm saying terawatt, that's joules per second. So I'm going to say energy equivalent. So the way I like to think is the world in 2012 was burning a 16 trillion watt light bulb. It's on all the time, and you got to give it energy to keep the light bulb on. The nice thing about watts is that you don't have to worry, as Nocera talking about, a day or a year, because it's energy per unit time. It's the energy rate of use. So in 2012, you're using 16 terawatts. I can go through this equation and calculate what your future energy needs are. And by 2050, I can tell you you'll need 16 terawatts. Now, to do that calculation, I had to make one assumption only. The world population will be around 10.2 billion. So I know that number. GDP per capita, I can do a global average. It turns out if I take all the economies for the last 100 years, the gross domestic product globally grows around 2.3% per year. All right? So I can take that number for that, but I have to make an assumption here. And the scary assumption I made to get to 16 terawatts is by 2050, science and engineering will have developed new systems to allow us to save every bit of energy we use today. So in my calculation of energy intensity, I assumed you were going to conserve all the energy you use today, meaning you'll be conserving 16 terawatts. You won't, because we never do the right thing as a society, but I'm hoping you will. And by the way, I'm going to say you a lot because I've become so discouraged I've separated myself from society, so just ignore that. That's a psychological problem. So by 2050, you're going to have 16 terawatts of energy if you save every bit of energy you use today. If you don't, the number's going to be 32. And that's going to be very hard to get to. So if you're being a good society, conserving all your energy, why do you need so much more? And because it has nothing to do with this part of the world, the developed world. It has to do with the poor. So there's 6 billion new energy users coming on board in the next 40 years. There's 3 billion low energy users. Right now there's 1.6 billion people who haven't seen an electron in a wire ever. And the 3 billion that are coming and being born in this part of the world. So by 2050, you're going to have 6 billion new energy users, and that's what's driving that number here. Now, our argument is if you don't take care of those 6 billion with the right energy, meaning as a scientific community, don't provide them an option for renewable energy, and they start using coal, oil, and gas, you will not have a sustainable planet. So our target was, can we do science for the poor? Meaning, and we'll get into this, it's a different type of science you need to do. It has to be low capital expenditure. I'll explain that in a minute. It can't be systems that cost billions of dollars because those societies are poor, so they can't afford billion-dollar energy systems. And I'm going to claim it needs to be distributed. And the reason for that is if you're poor, you want to have access to energy. There is one energy source, in case you've never realized it, she follows you around everywhere you go. You can look up at her. She's there for everybody, the sun. And she talks to you. I'm going to tell you, SEI was interviewing me today, and they said, you have a relationship with leaves. I also have one with the sun. When you feel her being warm to you, realize she's talking to you, saying, use me, use me, use me. And so if you're poor, you have the sun following you around. So it's available to everybody. That's important. And the final piece is if you're going to be low CapEx, you have to be simple. You can't have heavily engineered systems. Heavy engineering comes at high initial cost, high CapEx. So you want to be simple engineering, and now I'm going to make a jump. I'm going to tell you, doing Google research again, that simple engineering means lightweight and highly manufacturable. So what do I mean by that? So here's a manufacturing curve. If you take Manufacturing 101, you learn about manufacturing costs. So if you take a manufacturing engineering course, you'll learn about things like this. And what this says is manufacturing cost, how much does it cost to make something? But I normalized it for its weight. That's it. How much does it weigh? All right? And that's the y-axis. And then I said on the x-axis, how many do you make a year? And you can see I've related different things, and they all fall on this curve, no matter what they are. So a Boeing 777 and an automobile are on the same manufacturing curve. This doesn't work for IT, intellectual information technology. That's low CapEx. Intel chips aren't made this way. It doesn't work for pharma, pills. It doesn't work for commodity chemicals. But it works for machines, and energy systems are built out of machines ultimately. So that's a manufacturing curve. You could say these are kind of all the same, but it works for anything that's heavily manufactured. This is true. It turns out McDonald's has a CTO, a Chief Technology Officer. They really do. And I met him 2 years ago, and I asked him, how much does the hamburger weigh and cost to make? And there it is. The only thing here is I only have it at 100 million per year, and I think the number's closer to infinity. But outside of that, so I've related a hamburger to a Boeing 777. This is a real number. And this is an interesting number if you're a material scientist. You never get cheaper than $10 per pound. So if you're ever doing material science to try to replace something at a systems level, you should just price it out. The closer you are to $10 per pound is the closer you are to going to market. That's interesting. But why is this curve informative? Because the way we build energy systems is at the other end of the curve. You only build one of them. They're very heavy, and when you take very heavy times $10 per pound for an energy system like this, a power plant, it comes out to around $1.5 to $2 billion. Now, if you're poor, no investor is going to put $2 billion investment to build your energy system because you'll never get a return on investment quickly. That's why the poor parts of the world haven't reinvented our energy systems, because they can't. The danger is you don't want them to do that in the future, so you need to give a different option as a scientist. And we have simple thinking. If this end of the curve isn't working, turn your eyes to this end of the curve. So I'm not kidding you, students out there. Using this analysis, I'm telling you, we're setting our science problem. We wanted to make the McDonald's hamburger of energy. So just keep that in mind. And it's got to be made like a hamburger. So I'm going to convince you you can make an energy system like a hamburger. Now, what is lightweight, cheap, and highly distributed? My friend, the leaf, right? So they're everywhere. And what a leaf does when sunlight hits it up front, I'm going to get yelled at by Stenbjorn Styring because I forgot to put my P in here, but Stenbjorn, every other slide has a P in there. So what happens is you split water to oxygen and hydrogen, but nature had a problem dealing with gaseous hydrogen, so it stored it in a solid form, NADPH, that's solid hydrogen. But what this leaf does up front is it takes sunlight and rearranges the bonds of water from the OH bonds in water to hydrogen and oxygen. In that chemical bond rearrangement, it stored sunlight in hydrogen and oxygen. At night, it can do it during the day, but it doesn't need any more energy. Once it has the NADPH, it can take CO2 and make biomass. That's a thermoneutral process. So the question is, can we do this? And I will tell you it's a tough job. So to emulate what a leaf does artificially, people have talked about it for a long, long time. This is a very famous paper from the Italian photochemist Chimichon at Bologna in 1912. And you can read this, and he was saying it would be useful to society if we could get rid of coal and oil and build a nicer civilization based on solar energy. And then he says, could we fix solar energy through the photochemical reactions that master photosynthesis? And that was in 1912. And that kind of tells you we haven't been working on it very well, because if you can read something from 1912 and it still makes sense, that's worrisome, right? So this isn't an easy thing to do. So what we did is we took a step back and said, how does photosynthesis work functionally without worrying about all the beautiful details of that photosynthetic membrane? And this is how it works. Sunlight comes in, and then the plant can't get its hands around sunlight, a photon. So what it immediately does is takes the sunlight and it does a charge separation. In physics lingo, it's called an exciton. So once the photon hits, an electron heads one direction, that leaves a positive charge behind. The positive charge goes the other direction. So in the photosynthetic membrane, it's capturing the light above it with light harvesting complexes, then funnels the light into what's called a special pair where the electron holes separate, and then that beautiful membrane is designed to move the electron and hole away from each other and not have it short circuit. At that point, it puts the electron in a cofactor, an iron reductase, and on the positive side, it puts it into a manganese cofactor. So you put a negative charge in one complex, a metal of a cofactor in biology, and then the hole's gone into another cofactor. This is important to understand. At that point, the leaf is a battery. That's what you do with batteries. You store charges on metal centers and you take the charge out. But photosynthesis knew batteries have limited energy density. So if you just look at the physical nature, you can't put holes in electrons. You have to put them on metal centers. If you look at the physical density of material, you hit an upper limit with a battery. The plant needed to store a lot more energy. So it does it 4 times. It will have photons come in, and it puts 4 holes and 4 electrons in cofactors. It looks like a battery. But then it takes that battery charge, it's an energized battery, and then it operates on water and drives the splitting of water, and that's a 4-electron, 4-proton process. When you split water, you have O2, it uses 4 holes to split water, and then it leaves 4 electrons and 4 protons behind. Then that's combined to make nature's NADPH. So it does water splitting this way. If you think about it as a systems engineer, it's light in, energize current, store it in metal centers, and then run the chemical reaction of water splitting. That's a complicated reaction, and I won't go into it today. We actually spent 15 years of our life studying how protons and electrons couple. And as a matter of fact, I see Leif Hammerstrom here, one of the world's experts from Uppsala in proton-coupled electron transfer. And that is that an electron is quantum mechanical, it spreads out. A proton is classical. And so this coupling of a quantum mechanical entity to a more classical one is very complicated. But science, due to work like Leif has done, has taught us how to, in work we've done in our group, it's taught us how to couple protons and electrons. If you do that efficiently, you get a low energy process and you can split water efficiently. So what we said is, could we do the same thing? We'll take a material, have light come in, we'll do charge separation, we'll do it 4 times, and then can we store that in some catalyst that then, after it's energized by 4 electrons and 4 holes, it will act on water to split it to make hydrogen and oxygen. And then, in the last few years, matter of fact, the last 2 years, we said, could we go the distance? Because, as I said before, photosynthesis doesn't stop at water splitting. It fixes it with CO2 and makes biomass. So we set out to do that. Now, this idea of charge separation to split water goes back to the 60s, a famous experiment in Japan using titanium oxide in 1968. The problem there is that's how the whole science community went. It's called a liquid junction, photoelectrochemical cell. Now, 50 years of research went into, can we make a material that when we shine light on it, it will split water? People weren't listening to photosynthesis. Photosynthesis did charge absorption and separation with this photosynthetic membrane. It does catalysis with cofactors. The problem is a good semiconductor, when you do this 1-electron hole charge separation, does it one electron, 1 hole at a time. The catalyst I just told you does 4 electrons and 4 holes. So what makes, if I put 4 electrons and 4 holes and protons in my semiconductor, semiconducting physicists will call that a defect site. And that is a place that the hole and electron can recombine. And so the problem with a 50-year strategy of a liquid junction photoelectrochemical cell is that what makes a good catalyst makes a bad semiconductor, and what makes a good semiconductor makes a bad catalyst. So after 40 years of research, guess what? Nobody came up with a magic material that could absorb the light, do charge separation, and do catalysis, all with one material. So we listened to photosynthesis and said, how about this? We'll do a Berry junction. We'll put the photovoltaic material that does charge separation between 2 conductors. Then the electron can go up here, pass through the conducting layer, and we'll make a catalyst to take 1 electron. And then we'll make a catalyst to take the hole left over, and we'll store it there. And then we'll do it 4 times, and we'll split water. In this design, I've separated the semiconductor from the catalysis, so I can optimize both of them independently. So that was a big change from what people were doing before, this Berry junction. That allowed us to say, can I make a good hydrogen catalyst? Can I make a good oxygen catalyst? And how do I integrate it to the photovoltaic? And the hardest part is the first step, splitting water to make oxygen and leaving the 4 protons and electrons behind. So we set out to do that. And Matt Cannon, and this is 2008, showed You could oxidize cobalt-2 to cobalt-3. So cobalt is, if this is the periodic table, cobalt's right here. It's on the right side of the periodic table in the transition metal series. And so when you oxidize cobalt, take one electron from cobalt in solution, you make cobalt-3. In the presence of phosphate, you get a thin film on the electrode. And we did a lot of experiments. We could go to do synchrotron radiation at Stanford, and we could shine high-energy synchrotron radiation as the catalysis was going on, and we could figure out the structure. And the structure is this. The cobalt gets stitched together with oxygens, and it makes this cluster of cobalt atoms. Now, what's interesting about this cluster is this is the cofactor, the simplified line drawing of the cofactor of photosystem 2, the one that does water splitting. It's called the oxygen evolving complex with manganese. And that is a cubane, so it's a cube of manganese and oxygens, and then this manganese has a famous name in the literature. It's called the dangler, because of a man named David Britt. So if you take that cubane, and now I take it and do a head-to-tail dimerization. Now I'm going to put cobalt in place of manganese. I rotate it by 45 degrees. I get that. So it turns out, structurally, this looks like the oxygen evolving complex. It's catenated cubanes. It self-assembles. You don't have to do any synthesis. You just have to put current in solution, oxidize cobalt-2 to 3. You don't need to know any chemistry. It will spontaneously make this once you get this to cobalt-3 in the presence of phosphate. That's what happens in the oxygen evolving complex. The plant takes manganese 2 to 3, and that cubane spontaneously self-assembles. It has the same proton-electron inventory to split water. In this compound is photosystem 2, oxygen evolving complex. I won't go into that today. And the most important thing is it's self-healing. It fixes itself. And in the plant, the oxygen evolving complex is self-healing. Now, in chemistry, we don't make self-healing catalysts. What we do is we run a catalyst for a period of time, and then it dies. And then what we do is we regenerate it. All right? And that's how our catalysis is performed. Believe it or not, this is the first catalyst that's self-healing. This cobalt catalyst never dies. We set up the chemistry that as it's operating, it's always doing the self-assembly process. So if some of it starts to fall apart, as it's operating, it actually can re-self-assemble itself as it's doing water oxidation. Another way to say this is, in this field of catalysis, you always hear the word turnover number, which means how many times does the catalyst turn over before it dies? And all catalysts have a finite turnover number for if you do repair. In self-healing, the turnover number is infinite because it's never dying. It's always fixing itself as it's working. And this is my only really ugly chemistry slide. But I just want to give you a feeling about how it works, because this took a long time for us to figure out. And you're going to find out that all of the science I'm about to tell you is due to one discovery, a self-healing catalyst. Because here, this blue line right here is the catalyst making oxygen. And so at a if I'm at pH 7, at a voltage of 1.2 volts, you need 1.23 volts to split water to oxygen and hydrogen. So at 1.2 volts, the catalyst is making oxygen. This red line is the curve for self-assembly. And so what you find out is if I have a voltage of 1.2 where I'm splitting oxygen, I have plenty of extra voltage. If any of the compound decomposes, it can get oxidized back to cobalt-3 and re-self-assemble. So in this entire green area, and this is pH, from 5, this is acidic to slightly basic, but it's around neutral water, this catalyst self-assembles. Now, why is that important? Remember what our goal is. We want to go to the pore. If I have to make an energy system that needs pure water, how am I going to distribute pure water to everybody who's poor? This catalyst, you can use any water source. So you can use pure water. We've used the Charles River. You can use Boston Harbor. You can use urine. And because it will fix itself if there's defect sites through the self-assembly process. That's interesting, and I'm not going to talk about it today, but if, say, you use urine and you split it to oxygen and hydrogen, when you recombine oxygen and hydrogen, what do you get? Clean drinking water. So there's even an extra bonus here. Not only do you have a way to do distributed energy storage, you also have a way to do water purification in a distributed way. And it's all because of self-healing. That's important. The other thing self-healing does, I can now operate in water. Before this research, everybody used concentrated base. And concentrated base is very harsh, and you have to have a lot of engineering to use harsh conditions. Now I can use simple, remember simplicity. I don't need to do a lot of engineering. I can use a glass of water. That allows me to do facile integration. I'm going to now integrate the water splitting with the semiconductor. And as you'll see by the end of the talk, I can couple the biology. So what we did is we took the catalyst, and now we're going to make oxygen. When you make oxygen, we were going to put it on silicon. Silicon is what's in your solar panel. So when sunlight hits silicon, you do charge separation and use the current. So I'm going to use the silicon that you use in a solar panel. But now I'm not going to wire it up. I'm simply going to put a coating on it. I need to put a protective coating. This is fluorinated tin oxide. Because when you make oxygen, oxygen plus silicon makes SiO2, sand. So I don't want to decompose my silicon to sand. So I put a protective layer on it, again, by coating. We can use a simple thing called chemical vapor deposition, just gaseous material will make a hard coating. And then we put our catalyst on top of it. Now, silicon, a single junction, one flavor of silicon, puts out 0.57 volts. Water splitting's 1.2 volts. So in this configuration, if I use a single junction, I don't have enough voltage to split water because I only have 0.6 volts when I need 1.2 volts. So we had to put contacts. We did this in 2011 and put contacts here so we could put extra voltage into the silicon. And then what we did is we just dropped it in water, and we did what I told you we did before. In cobalt-2, we just have the silicon now with our catalyst, or our coating. When we oxidize cobalt-2 to 3, you make the catalyst coating. And so here, this is the self-assembly process, and then this big wave here is where you're making oxygen. You're passing lots of current, because all the current's going into oxygen. And so this looks like an electrode. This is what you would do in electrochemistry. Now, here's the curve I just showed you in the dark. The special thing about this electrode is I have silicon. So when I put sunlight on it, I internally generate 0.57 volts. And I separate an electron in hole through a potential of 0.57 volts. So now, when I take that electrode in the dark, it takes 1.2 volts to start splitting water. When I now put it in sunlight, I don't have to push it as hard. As a matter of fact, you can see at any driving voltage I use on the silicon, once sunlight is shining on it, I reduce the amount of extra voltage I need to put into the silicon by 0.5 volts. So now you can start thinking, well, if that's what one junction does, what happens if you string a few of them together? And that's what we did. We made a triple junction. So this is amorphous silicon. Amorphous silicon absorbs 400 nanometers. And amorphous silicon has a strained lattice. That's why it absorbs in the blue spectral region. And then you can start doping germanium into it. And germanium's a bigger element than silicon, so the strain lattice relaxes. And depending on how much germanium you dope into it, I can take that curve and move it anywhere I want in the absorption spectrum. So we dope enough germanium in this middle layer of silicon to get that absorption band. Then you dope more germanium into it, and you get this lowest energy band. Now, why did we do that? Because this absorption profile is this plus that, or this. And if you look at that absorption profile, it's covering the solar spectrum. So that's allowed me to engineer the light absorber separate from the catalyst. And I can completely cover the solar spectrum and absorb all the light from the sun. And then it turns out, this is 0.5 plus 0.5 plus 0.5, so you get around 1.5 volts of voltage. So I have plenty of voltage now. I don't need to put any external input in. And now I coat my catalyst here. And so I talked to you about this catalyst. This is the cobalt catalyst that makes oxygen. We made a nickel molybdenum zinc alloy, a thin metal alloy, which collects the electrons to make hydrogen. And now this works just like a leaf. This is why we called it an artificial leaf. Sunlight comes in, you do one electron charge separation, and then you do it a second time, a third time, a fourth time. And then when you get to 4 times, the cobalt gets charged up and does that proton-coupled electron transfer reaction and splits water to oxygen. And then, let's see, there it goes. So now what you're seeing is the holes are coming up here. Once this gets 4 holes, it splits water to oxygen. The electrons have gone to the other side, the back side, and they get collected by the other catalyst, and the protons that are made that are left over in solution get combined back here, and that's making the hydrogen. And this really works. It's so neat. You can take this, just drop it in a glass of water, walk up to the window, and you'll see oxygen coming off one side and hydrogen coming off the other. No other inputs, no wiring. It's just silicon coated with catalyst. I told you I was going to make a hamburger. Amorphous silicon is the hamburger patty. The protective coating's the cheese. The cobalt's the top bun, and the bottom is the hydrogen. And I'm serious. This looks like a hamburger. This is what I wanted to do because there's no wiring. It's very simple to manufacture. You just take silicon and you put coatings. And the coatings you can make by chemical vapor deposition. So this looks like a hamburger, which I can now hand out to everybody. They can go find some dirty water, drop it in there, and make hydrogen and oxygen using sunlight that's following them around. And if they don't have any water, they can use urine. So that's a huge advantage. And I don't have to ship in any water. So this is my hamburger. I told you, this is my only goal in life was to make a hamburger, the McDonald's hamburger of energy. So that's what this looks like. Now, we felt pretty happy. But then what happens? Now we're going to get to techno-economic problems. I give you a bunch of hydrogen. What will you do with it? What do people do with hydrogen? They blow up balloons. That's the only thing you will do with hydrogen because there's no infrastructure for hydrogen. You could use it because we have fuel cells, but we don't have a large infrastructure to accept hydrogen. And photosynthesis couldn't deal with hydrogen either. It then conveys hydrogen with CO2 to biomass. Now, I told you before, water splitting's done with sunlight because you've stored 1.23 volts of energy in using the sun to do water splitting. Once you have hydrogen, and I've separated hydrogen to proton and electron, any reaction you use hydrogen with to CO2 to make a fuel, this number means it's all thermoneutral. You don't need to have any energy input. That's why the plant can fix carbon at night. It doesn't need the sun. Once it uses the sun to split water to get hydrogen, it's good to go. It can make any fuel it wants through biomass. So we realized that and said, can we do the same and do it better? Because the one problem photosynthesis has is it absorbs 2 photons of light. So I can do the amount of energy absorbed, and then it makes oxygen and NADPH. And so I know how much energy that is. So energy in to NADPH and oxygen, it's 28% efficient. But then the plant isn't like my silicon. It can't absorb the whole absorption spectrum. So when I integrate the whole absorption spectrum relative to this, I find out it can only it can only make biomass at 10.5%. Theoretical limit. That's it. It can't do better, a plant. I've taken care of that problem because here I can absorb the whole solar spectrum. So I freed myself of the limitations of the plant. So now here's photosystem 1 and 2 schematically. This is what I talked about before, the membrane absorbing the light, doing charge separation. Then it makes NADPH, and then from NADPH it makes ATP, and from ATP it goes in the Calvin cycle and makes biomass. But look at what I just did. I'm making hydrogen. So if I can take hydrogen and get to NADPH, I don't need the sun. I'll use my artificial leaf to make the hydrogen, and then I'll feed the hydrogen to a bug. I'll take a bacterium, and we took a bug called Ralstonia eutropha, and what I'll do is genetically engineer the bacterium to have a protein in it called hydrogenase. It's an enzyme, and that hydrogenase, its function is to take hydrogen to 2 protons and 2 electrons, which then gets coupled to a thing called the NADPH reductase to make NADPH, and that gets coupled to ATP synthesis. So if I can take a bacterium and genetically engineer a hydrogenase into it, it can eat my hydrogen and make ATP, and I should be able to do photosynthesis. But I'll do it without the plant absorbing the light and making hydrogen. I'll use my artificial leaf. So we did that a year ago, and what you do is you get to this special branch point out of the Calvin cycle. It's called acetyl coenzyme A, and from here you go to biomass. And we did that. These bugs, these genetically engineered bugs, only eat hydrogen. That's this only food source. We don't give them anything else. We put phosphate and nitrate in solution because they need it for DNA synthesis and protein synthesis. But then we never give them any more phosphate or nitrate because when the bugs die, they release their nitrogen and phosphorus and another bug takes it up. So the only input in this after it's initially charged is hydrogen. That's their food. We give it no other food. And they make biomass. We can also play another game. I can put different genes in here, and I put 4 new genes in, and I put these genes in, Pha A, CTF, ADC, ADH. I don't want to get into genetic metabolic engineering. But you put those 4 genes in. Why do I put those 4 genes in? Here's acetyl-CoA. I have to break this bond. You do that with a protein, a ketodiolase enzyme. The Pha A gene puts a ketodiolase in. Then I need to do I got to couple 2 carbons. I got to couple that to that. That's done with this enzyme. I put that gene in. Then I get rid of carbon dioxide. I put that gene in. Then I hydrogenate it. And all of a sudden, I'm not making biomass. I'm making a liquid fuel, isopropanol. And we did that. And we found that our biomass efficiency, sunlight into biomass, was 1.6%. And if we use this other engineered system, genetically altered system, we could make isopropanol at 0.6. That made us happy. It showed that we could do it, but those efficiencies aren't great. I'm at the efficiency of regular photosynthesis. And so we started wondering why. And your efficiency depends on how much voltage you put into the system to make hydrogen over the thermodynamic efficient number for hydrogen. So it's 1.23 volts. So if I'm at 1.23 volts, I have potentially 100% efficiency. If I'm at 2.5 volts to make the bugs work, to make hydrogen for the bugs, then it's 2.5 over 1.2. My maximum ceiling's 50%. And the bigger this number gets, the lower my efficiency becomes. It was really interesting, but when we first did these bacteria, we had to keep them alive by putting 2.7 volts in them. So that's weird. You don't usually electrocute something to make it live. And we found out if we use the lower voltage, this is the growth culture of the Ralstonia. If we went below 2.7, so here's the Ralstonia living, Once we went below 2.7 volts, they died. So that was weird. Why is that happening? And this is what we figured out. On the hydrogen side, where you're making their food, the Ralstonia is in with the artificial leaf, you're making food. If you don't have enough voltage to overdrive water splitting, what happens is the potential before you make hydrogen, you can reduce oxygen from the atmosphere, and you make superoxide. And that makes what's called reactive oxygen species. That superoxide can go to peroxide and attack the DNA of the bacterium and kill the bacterium. So what we had to do, we didn't have a good catalyst system for the bug. It wasn't biocompatible. We had to be at 2.7 volts to direct all the current into making hydrogen. When we got lower, the current got sidetracked to make basically a toxin to kill the bacterium. So we did two things. I'll be done in a minute. We took a bacterium. So here's the beauty of biology. I can then take the bacteria and challenge it with superoxide. They died, they died, they died. A few of them started living, a few more started living, a few more started living. Guess what they did? They genetically altered themselves, the smart ones, to combat ROS. And what we found out, we genetically profiled it, and we found out the bug did a 45 base pair deletion, and it was a membrane efflux gene. It was a gene to let things into the cell, and the superoxides were coming in there. Once the bug eliminated it, it could live in the presence of ROSs. So that's one approach. We did a smarter thing. We made a different catalyst on the hydrogen side. This is cobalt with a phosphorus alloy, and that catalyst doesn't make superoxide. So these catalysts and my other catalyst made superoxide. This one's making no superoxide that gets translated to H2O2. So that one, if I use this catalyst system, cobalt phosphate and cobalt with the phosphorus alloy, the bugs are perfectly happy. That allows us to drop way down in voltage, near 1.2 volts. That ups my overall efficiency. So what you do, this is how the experiment works. You take a few genetically altered bugs, throw them in solution. You then give them hydrogen, and they go into an exponential growth phase, and you let them grow. You get to whatever optical density you want, concentration. So we get to an optical density of 2. And then what we do is we control the amount of hydrogen to go into steady state. So the bugs aren't growing anymore. Some are dying, but others are being made, so we have a steady state concentration. And then we take the excess hydrogen and feed it into that metabolically engineered pathway. So what the bug wants to do is use hydrogen to keep growing exponentially. But we control the hydrogen relative to the hydrogenases we put in the bug. And then we use the extra hydrogen to go into that pathway to do CO2 reduction to make isopropanol. And so here, this was published in Science in June. We can hit, first off, if we just let the bugs grow wildly and make biomass, this is sunlight into the amount of biomass, it's 10.2%. And remember, the best crops are 1%, microalgae's 3%. So we're a factor of 10 over natural photosynthesis now in making the biomass, the lipids of the bug. But then, if we take the other engineered bugs, we can make isopropanol at 7.2%. We can do different genetic modifications, make isobutanol, isopentanol, longer chain carbon, more valuable fuels. We're up at 5% for those. Look at this one. We can put in genes to make plastic. So we make bioplastic, polyhydroxybutyrate, 8%. So we're way over natural photosynthesis now, using the artificial leaf with this engineered system. You can even make long-chain hydrocarbons. I don't want to get into it. But in this acetyl-CoA chain, if I use the thio, I can have it just keep adding 2 carbons at a time, 2 carbons at a time. And then I use an enzyme called the thioesterase to pull out of the Calvin cycle. And depending on what thioesterase I use, I can pull out at C4s, C8, C12. If I want to get odd-chain hydrocarbons, I go to a propionyl CoA that has 3 carbons, and then you add 2 carbons at a time, and you get odd-chain, long-chain fuels. So you can make big fuels here. These bugs, a 1 liter reactor with an OD of 2, meaning 99% of the light doesn't get through, those bugs concentrate carbon dioxide naturally. You'll fix 500 liters of carbon dioxide per day with just a 1 liter reactor of these genetically altered bugs eating my hydrogen from the artificial leaf. And remember, my efficiencies are high because the artificial leaf is high, and to beat out the problems of photosynthesis for water splitting. The advantages of this is I don't have to do CO2 concentration. The bacteria have natural carbonic anhydrases that pull out CO2, just like grass, right? You have 400 parts per million CO2. That's not much CO2, but they're pulling in a lot of CO2 because they have natural mechanisms. I don't have to concentrate the biology does it. Because of my separation of artificial leaf with the bacterium, unlike algae, my bugs don't need to see the light. I have my artificial leaf seeing the light, and that's splitting water at 12.8% efficiency. The hydrogen, the bugs are operating in the dark, so I can pipe the hydrogen into a vat. So that means I don't have to pump water, and I don't have to have glass tubes. So my reactor design goes way down, and I'm a factor of 3 over microalgae from a techno-economic analysis. I'm not using any land that you would use for crops. So I'm not competing with land resources, and I need area that's a factor of 10 less than crops because I'm splitting hydrogen at 10 times more efficiency. So this looks like a pretty good win-win-win-win situation. Finally, I just want you to realize, what was our trick? Our trick was to genetically engineer a bacterium to have a nose for hydrogen and eat hydrogen. And I put in genes to make fuels, because I'm an energy person. But I could put in genes to make anything. This is a general renewable carbon neutral synthesis platform. So I could, like I already showed you, we put genes in to make plastics. You could put genes in to make polymers. You could put genes in to make drugs. I'll tell you what you should keep your eye out for my group this year. I can put a gene in that puts a nitrogenase. Nitrogenases take nitrogen out of the atmosphere, and I can combine the hydrogen from my artificial leaf, and I can make fertilizers. So I can start doing distributed food for the poor now with this approach. So keep your eyes out for that. It's working. I'll just give you a hint. It's working. So this idea of putting a nose on the bacterium for hydrogen is very powerful using renewable energy. So in doing this, we had to do a lot of different things, but I just want you to start with the basic science discovery. By making a self-healing catalyst, I could operate in water, and once I was operating in water, I could easily integrate the silicon to make the artificial leaf, and since I was in water, I could easily interface to a bioorganism to make the bionic leaf. So that's what we did to do this. And then finally, and this is just as a jump-off point, this is the last slide for later, how do you get this to the poor? The way you usually do it is you start a company, and then you try to get investors, but then they say, what's our ROI? And it's for the poor. They don't have a lot of money, and your investors get upset. And they don't have patience. So what we're doing is we've integrated our science program with a policy program. The IP, all the intellectual property, I convinced Harvard to pass through, and we're passing it through to India, because I want to start in India first, and they're going to own the IP and let them develop it and do reactor design. But they still need money, so what we did is, and you guys could do this, you scientists, we put in, and I'm working with Michael Greenstone, a famous economist at University of Chicago, and Rohini Pandey. This is really what they're doing. What they do is they put light scatterers in carbon emission plants, and so you know exactly how much carbon is being emitted from different plants. And then what they can do is set up a cap and trade to generate revenue, which can then get fed into the discovery piece for the science and engineers to do scale up with the free IP from Harvard. And so we have, and then we're going to let the people in that country acquire wealth off of this. because you want that invention to be there. So that's where it should be developed. And so that's my new experiment. I can't tell you if it's going to work yet. And will it accelerate this going to market quicker than the conventional one? We'll find out. But this shows you where policy can become very tied to discovery to accelerate technology transition and the part of the world where you need it most, the poor of the world. So with that, I would like to thank you for your attention.